So when a rock is thrown in the air, it's got an initial velocity given by this 40, which would be in feet per second. It's got an initial height, so when the rock left the person's hand, it was at a height of 6 feet. And then this is the gravitational pull of Earth bringing the rock back down to the ground. So in general, the picture would look something like this over time. We've got the height starting at 6 feet. The rock goes up. Gravity, of course, eventually pulls it back to the ground. So then we've got this time interval given. It says when you go from 1 second to 2 seconds, on average, how fast was the rock going? So I could get a little more accurate graph rather than my sketch. So negative 16, I'll use x is squared, plus 40x plus 6. And then for the window, x is time, so perhaps 0 to 10 seconds. And the y value stands for the height. Well, if it starts at 6, then maybe it's going to go up to, I'll guess, 30 feet. Well, not bad. It went a little bit higher than that. 35 feet. Okay, so at 1 second, it's up here at a height of 30. So at 1 second, it was up here at a height of 30. And at 2 seconds, it's at a height of 22. So what the first question, or part A, is asking, what's the average velocity? So as it moved from this point over to this point, if we could find the distance that it traveled, which actually would be along this curve, and measure that distance and divide it by the 1 second that it took to move from here to here, we would have a velocity. The distance over time is velocity. Well, we don't at this point have a way to measure this arc length. That's covered in about 2 more chapters. So instead what we do is say, well, what if the object had made a straight line? And we'll use that as an estimate for this distance right here. So what we need to do is find out what was the height after 2 seconds, and what was the height after 1 second. Subtract those two, which is going to be a distance of 8. Or in other words, it went from a height of 30 down to a height of 22. And it took 1 second to do that. So what we're really doing is, from beginning algebra, saying this is a line. Well, find the slope. The rise over run. So that's what we're doing here. Here's rise divided by the length of this interval is, of course, 1 second. But it comes from subtracting the two numbers, 2 minus 1. So then we can label this velocity average. And then to show my work, substitute a 2 into this function. So it's going to be negative 16 times 4 and a 40 times 2 plus a 6. And then substitute a 1 into the function, so that would be a negative 16, a 40, and a 6. And it gets divided by 1. And the units for the distance are in feet. I know that because this is the acceleration due to velocity in feet per second squared. If this was a 9.8, then we would be dealing with meters and seconds, but instead it's feet and seconds for the units. And now I need to verify that this is going to be a 30 minus a 22. So in here we've got negative 64, an 80, and a 6. And then let's see over here, if I combine this and this, it's going to be negative 10. So subtract, and that'll be 30. And then this should simplify to be a 22. So we've got, let's see, 86 minus 64. Sure enough, seems like a 22. So we've got 22 minus 30 feet in 1 second, or in other words, negative 8 feet per second. So the negative means that it's going down. Sure enough, that's a negative slope. It goes down. So it's going down at 8 feet per second on average. And now for even more fun, estimate the velocity as it hits the ground. So for one thing, we have to figure out when does it hit the ground, and then go back and do this idea at that particular time, rather than just the interval from 1 to 2. So first of all, when does it hit the ground? Well, that's at a height of 0. So use 0 for the height. And then use the good old quadratic formula to solve for t. So negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So that's going to be, inside the radical, that's going to be 40 squared, and then 2 negatives will make a positive. 4 times 16 times 6. So we need the square root of 1984. And there are 2 answers, but we only need the positive answer because we're dealing with time, so we only need the positive answer. So actually, if we get rid of this plus sign, then we would have the numerator would be negative, and when you divide by a negative 32, it's going to be positive. So we've got negative 40, and then subtract the square root of 1984 divided by a negative 32 is a positive 2.64, and I'll use 3 decimal places, 2 seconds. And I can verify that by going back to the graph and put trace and type in the 2.642. Now since I rounded a little bit, this isn't exactly 0, but it's pretty close. If I would have used 2.6419, I forget what it was, the next one was, but then it's going to be a little bit closer to 0. So the next thing to do is, instead of using the interval from 1 to 2 like the first part, we've got so far only one number to use, 2.642. But the question is asking, estimate the velocity just as the rock hits the ground. So in the moment before it hits the ground, we could say go back, let's say 0.1 of a second to when it was 2.5 seconds. And then do the work like we did on part A, using this time interval from 2.5 seconds to 2.642. So it's going to be, we need the height at 2.642, which happens to be 0. We need the height right before that, 2.5 seconds. And then subtract these 2 times. So right now, to save a little bit of time on this video, I'm going to substitute the 2.5 to find out the height was 6 feet. So we would have this is a 0 minus 6, and then subtracting 2.642 and 2.5 is the result of 0.142. So this is in feet and this is in seconds. And so if we divide them, -6 divided by the 0.142, -42.254 feet per second.